So the second question, sort a binary array in linear time and constant space. Print all zeros and then ones. So what we will have, a binary array contains only zeros and ones. Okay, so here is the example given. Okay, so what we need to do is print all the zeros first, and then we will need to print all the ones. Okay, so what we can do for the constant space and linear time, um, we could iterate through the whole array and then count number of zeros and number of ones. That would be n minus number of zeros. So what we can do, we could directly print the array like that. Uh, First printing the number of zeros, printing zeros, uh, the number of times the zero came, and then printing number of ones they came. Okay, so uh, then there is so it takes a constant time and constant space, sorry, linear time and constant space. So now what is the other method? So place zero at initial position, the rest with ones. Okay, I think that is also doing the same thing. So what we have done here, we have counted the available numbers. We have put and incremented the E of I, and okay. So what we have done here, we have taken the whole array, and here in the pointer we have put I, and if the value of I is equals to 0, I and j, there are 2 pointers. Okay, if the value of I is equals to 0, then we are going to increment j. So what we are doing here, we are taking all the zeros and placing it here as we iterate through the array, and at the end we would be having all the zeros here, but it it would be missing all the ones. So what we'll do, we will fill the rest of the places with one. Okay, so that's the pseudocode here that we have. We have taken a constant I, sorry, j, or available, anything you can take. Okay, so I iterating from I to n, and we will have a of I equals to 0. Then we will, what we will do, we will take this available position, and we will give it the value of 0 and increment the available position by 1. Okay, so what we'll have here, up till this point, number of zeros, let's say 1, 2, 3, 4. There are 4 zeros. Okay, so j's position would be here, and up till n, there are we have iterated through n. Okay, but there is no more what you could say zeros anymore. Okay, now what we need to do, we will iterate from available position, that is j, to n, and we will fill all the elements in the array with 1. Okay, so that is one of the method. So the third method is the one that is required here. This method is called partial logic quicksort. So quicksort is one of the sorting algorithm. Uh, if you don't know, I'm going to explain quicksort here. Okay. So quicksort is a in-place sorting algorithm. It's 2 to 3 times faster than merge sort or heap sort. We will cover that later. So here for quicksort, what it does, what's the principle behind it? It is going to uh, make the comparison and sort them as per that comparison. So if it's less than comparison or relation, then it will sort accordingly. Okay. So average sorting time for this algorithm is O of n log n, but the worst time when you have taken uh, the pivot point not the correct pivot point, then it will take a long time. Okay, so that complexity would come to O of n square. So the principle behind this quick sort is divide and conquer algorithm. And what we are going to do, we will divide the whole array into smaller subarrays, and we will sort those subarrays. Okay, and we will do this recursively. Okay, so first of all, what we need to do here is take the pivot point. Okay, so pivot point is that point at which we will be uh, with the reference to that point, we will be moving the elements in the array. Okay, so we generally take it the leftmost or the rightmost. Okay, and then what we need to do is partition. Okay, so we will be reordering the elements in the array as per the pivot point. Okay, and if the element is less than the pivot point, it will move to the left of it, and if the element is greater than the pivot point, then it will move to the right of it. Okay, and we will do this recursively. So it would be better understood with the help of code. Okay, so let's say we have this array. Okay, 9 minus 3, 5, 2, 6, 8, minus 6, 1, and 3. Okay, so what we are going to do, we would be having three functions here. First is the swap. Okay, second is the partition, and the third is the quick sort itself. Okay, so for doing quick sort, what we have done is we have this is quick sort is the recursive algorithm uses recursive. Okay, so what we have done, we have taken if the start is greater than or equal to the end point, then we will return it. Okay, that means that's the end of quick sort. But what we have done here is we have taken another function partition, and we have given it the array, the start point, and the end point. Okay, so we have also parsed the same, the first element and the last element in the quicksort. Okay, so what it will do, the pivot point will be there. Okay, so we will what this partition will do, it will return the pivot point and will arrange the whole array uh, as per that point. So uh, as per this pivot point, it will be having the left elements as less than the value of the pivot point, and the right elements more than that of the pivot point. Okay, so after that, we will be recursively calling this quick sort, and we will be sorting each and every subarray, that is the left part and the right part of the pivot, because the pivot point is at its right position. So we would be sorting all the other subarrays. Okay, so for the left part, we have taken the array from starting to the point pivot minus 1, and for the right part, we have taken from array from pivot plus 1 to the end. Okay, so coming to the quick sort for the partition. Okay, so how we are doing that, managing all the endpoints that all the points that are less than that pivot point to the left, and all the elements that are greater than the pivot point to the right. Okay, so what we have done here, we have selected the point that is at the end of the array as the pivot point. Okay, so first step is start. Okay, and then we have put a pivoting index. Okay, so this would be used later. Um, so this would be the point where the elements less than the pivot will move to the left, and greater than will move to the right. So what we have done, we have iterated through a for loop. Okay, and what we have done here, if the array is less than equal to the pivot, then we have swapped the index with the p index. Okay, so we will be taking the example here. So this was the array. 9 minus 3 is 6, 5, 2, 6, 8 minus 6, 1 and 3. Okay, so the value of I or is equals to start. So starting point is 0. So here you could see the value of I. Okay, p index is also equals to start. So its value is also at the start of the array. Okay, now we are going to swap the elements. Okay, so if the value of e of I is less than the pivot, okay, so the next element, that is minus 3, its value is less than the pivot. Okay, so pivot is the last element. Okay, so for the first element, 9 was greater than 3, so we have not moved 9, but we are going to move minus 3 because that is less than 3. Okay, so when the value of I is here and the p index will be there itself at the start, then we are going to swap it. Okay, so we will swap it. It will be like minus 3 and 9. Okay, and then we will increment the p index. So p index will move from here to here. Okay, now similarly it will iterate through the whole loop. So this will happen. Here we will get minus 3. After like moving this element, swapping these two elements, we get instead of 9, we got minus 3, and then we uh, have 5, 2, and all these things. After swap, we got this array. Okay, so after this, we got the pivot index here. Okay, at 6, and all the if you could see all the left um, elements are less than 3 and all the right elements are greater than 3. Okay, now here you see the value, the pivot that is equals to 3. Now what we are going to do, we will swap the end element or the pivot point with the p index. Okay, so we will be swapping 6, putting 6 here, and the 3 will come here. So what happened, all the elements are now arranged properly. Okay, like the left side is less than 3, the right side is greater than 3. So now uh, we have to return that pivot point. Okay, the pivot index, because we need the position of this pivot index to determine what recursively we will be sorting. Okay, so in the next sort, in the next quick sort, we will be sorting this one, and after that we will be sorting the right side of it. Okay, so this will go on, uh, and we will be having the array, complete array in a sorted manner. So the key point to remember here is this statement. Okay, so as per this condition only, we are sorting the whole thing. So if we alter this condition or we make any changes, so we will be having like two indexes, and uh, as per this point, we will be putting every element as per this condition to the left side. Okay, so this condition, this thing would be used in the partial quick sort, as you will see here. So here we have. Okay, so here what we have done, we have taken 1 as the pivot point. So what will happen, every element that is less than the pivot point will swap to the left side. Okay, so where is our, yeah, so this was our example. Sorry, 1 0 1 0 1 0 0 1. Okay, so uh, we have taken the pivot point as a pivot value as 1. Okay, so now we will be iterating through the whole array, and this is the index j or the p index that we used. Okay, so that is also here. So if the value of um, any value in the array is less than the pivot value, then we will be swapping it. Okay, so first here I came at the 0th position, the value is equals to pivot, no changes. Here the value is less than, so what will happen, we will be swapping these two. So here it will be 0 and here it will become 1. Okay, so again the I will move here 1, no issues. Again here yeah, pivot index also moved, so we'll be moving this pivot index to here. Okay, okay, so we have the pivot index here now. So after moving to this value of I, again we found the value is less than the pivot value, then we will again swap these two values. So this will again become 1, sorry 0, and this will become 1. Okay, now I again moves and we have incremented the pivot index. Okay, again we found 0 which is less than 1, so here again we swapped it. Again we got here and incremented it. Again we got 0, swapped it with okay. Now you could see our whole array is sorted. We got 0 0 0 0, 4 zeros here, and then 1 1 1 1, so 4 ones. And you could see we just use this condition to sort the whole thing. This is called a partial logic quicksort. Okay, so similar thing can be done for rearranging the even and the odd numbers in linear time. Okay, here we used like we iterated through the array only once, so the time complexity would be O of n, and we have not used any extra space like we used in hash map or something. Okay, so yeah, we could also do the same thing if the situation is like to put all the even numbers before the odd numbers and all something like that. So what we'll do, we will change the condition here. So if like a modulo 2 is equal a modulo 2 is equal to 0, then we would be swapping it, else we won't be. So what will happen, all the even numbers would be swapped to the left side. Okay, so